to explain these topics. Okay, so what is virtual memory? Virtual memory is when the size of the process is so large that it is not able to load to completely in the main memory. Then the concept called virtual memory comes into picture. So generally what happens, our main memory, because it is a costlier one, the size of the main memory is always in small, like 4 GB, okay, or 8 GB or 16 GB, in these kind of ranges, right? Whereas my secondary memory, where all my processes are there, my secondary memory, I get a lot of spaces here, 500 GB, okay, 1 TB, okay, 2 TB, like that. I am having the size of the secondary memory, and because the size of the secondary memory is too large, I can have here very big processes, suppose process 1, even smaller processes, but in, thousands of numbers, okay. And whenever I need to execute these processes, one thing that I have to do is I have to load it to main memory. Why? Because my CPU can access it from the main memory, right? So an CPU, which is a faster device, it is able to synchronize with the main memory, which is little slower than CPU, but much faster than the secondary memory, where my all processes are there, okay. So whenever I need to execute a process, I have to load it to my main memory, okay. But as I told that I may have lot of large processes whose size may vary in so so many numbers. Like if I'm taking one example of, you have been watching all those high definition movies or documentaries, right? So what is the size of those documentaries or movies? The size may vary from 4 GB to up to 10 GB to 20 GB, very high definition files, okay, media files mostly. So when I have to load it to my maybe 4 GB RAM, okay, one particular process is there having size 10 GB, I have to load it to my 4 GB RAM. How I'll do that, okay? So it is done by what, with the concept called virtual memory. Like to the user, the virtual memory gives an illusion that the entire process P1 of size 10 GB is in the main memory only, okay. Although at a time maybe only 3 GB or 3 GB of the 10 GB is there in the main memory, okay. But it gives an illusion that the entire process is there in the main memory, okay. So virtual memory uh, is able to give that feature to the user. It gives illusion to the programmer or the user that a process whose size is greater than the RAM can be executed, okay. So size of main memory is fixed and limited, whereas size of process can be anything, as we can see that. And we always want to increase the degree of multiprogramming by loading more and more processes into the main memory. So here in the main memory, if I am having only one process P1, then the degree of multiprogramming is how much? It is only 1. But if by putting some kind of intelligence, if I am able to load two process into the memory at the same time, okay, uh, by what kind of approaches? By maybe what is called, by maybe if when I use the round robin scheduling, I do multitasking only in a concurrent manner, okay. I give some time to process P1, then I give some another slot to process P2, again I give it to P1, again I give it to P2. So to the user, it gives the illusion that P1 and P2 are happening parallelly, okay. But actually it is happening in a concurrent manner, okay. I am assuming that I am having only one CPU, okay. So this context switch from P1 to P2, then again P2 to P1, it is very quick. It is so quick that to the user it feels like both P1 and P2 are happening at the same time. Okay, so uh, for this purpose also, why we do that? Because I always want to increase my degree of multiprogramming, and in it would is my 4 GB RAM. If I load P1 process, okay, if I am watching a movie, but at the same time some another process also you are running. Suppose you are running some program from your mini project that you are doing. Okay, while the program was running, okay, it takes maybe some time, some 1 hour or 2 hour, and during that time you want to watch the movie. Okay, so both the processes are happening at the same time, right? And to me, to the user, it gives the illusion that the movie is also running, and at the same time a program is also running. But if I am having only one CPU, that happens in a concurrent manner only. For some microsecond of time or nanosecond of time, the process P1 will execute, then P2, then P1, P2, like that. It will happen like that. Okay, so basically, as you can see that I load only some portion of the process to my main memory at one time. Okay, but to me it gives the illusion that entire process P1 is running, entire process P2 is running, and if I calculate the size of P1 and P2, maybe it is maybe 10 GB plus maybe 1 GB, right? But my RAM is only of 4 GB. Okay, so that is called virtual memory. The concept of virtual memory allows us to do that. Then the next concept is demand paging. So from the name itself, what you can perceive that demand paging, so some kind of paging has been done on demand. Okay, so what happens is, we know that CPU executes one page at a time, and I all this time I'm assuming that there is only one CPU is there, or there is only one core is there in the CPU. Okay, there are not multiple cores, so only one CPU is there, and that's why CPU is able to execute only one page at a time. So that's why we don't load. So why to load the entire process into the memory at a time? Okay, in case of a process larger than the size of RAM, it's not possible even if we want to bring the entire process into the RAM. So two things are there. One is that if my process length is larger than the RAM, I have only one option, that page by page I will load it to my RAM. Okay, another is also that since one page can be executed at a time, why I will load multiple pages at the same time. Okay, because at a time only one page can be executed, so that required page only I will load to my main memory. Okay, if I am having other slots, vacant slot in my main memory, I will give it to other process maybe. Okay, in that way my degree of multiprogramming will also be increased. So that's why what happens is, whenever a CPU will generate the request for a particular page, okay, that I will check in the main memory whether it is there or not. If it is not there, then I will load it from the secondary memory to the main memory. Okay, so that is called demand paging. So I am on demand whenever the demand has come from the CPU for a particular page. Okay, that time only I am loading that from the secondary memory to main memory. Okay, so we can bring only the required page or code segments into the RAM at a time. Okay, in case of page paging, I will bring that page, and if I am following the segmentation of memory allocation technique, then I will bring that particular segment. Okay, so loading the required page into the main memory on demand whenever page fall occurs is called demand paging. Okay, so another more concept or more terminology that you can see is the page fall. So whenever suppose CPU is requesting some page number 5, okay, it will check in the main memory whether it is there or not. If it is not there, then it will bring from the secondary memory. So when the CPU is demanding that page, it is called demand paging, and when that page is not there in the main memory, that is called page fault. Okay, it page fault has occurred because the page is not there in the main memory. I now need to bring it from the secondary memory. Okay, will see here elaborately. Here you see this particular diagram. There is this my CPU, and what I have, whenever the CPU requests for some particular page, then I check in my page table that uh, in that uh, in that page table which particular frame, okay, frame number 1, frame number 2 of the main memory is having holding that particular page. Okay, suppose as we have discussed in paging, this is the structure of a page table, right? Here these indexing 0, 1, 2, 3, these are the page numbers. Okay, these are the page number, and then the second column that were there, that were the frame number, right? But you see, as I have explained before also, that this paging technique, theoretically to explain, we can see that the page number is there and the page number is mapped to some frame numbers that will be there in your page table. But while implementing, we have lot of other things also to do. For example, you see in this page table, I am not only having the map frame numbers, but I am also having some tail to it. Okay, to this data structure called page table, I always have to include some header, okay, or some tailer. Okay, so this particular valid invalid bit, one more field is added, that is called valid invalid bit. Okay, and it will valid invalid bit. So it will tell us some information. Okay, some more information is there in the page table. So what is the case here in this scenario that you can see in this diagram? CPU is there, page table is there, fine. I am having a RAM, that means it is a main memory. Okay, whenever you see RAM, it is main memory or it is primary memory. And then in the RAM, definitely I will have that code segment of the operating system, and I am having this will be dedicated to the system program only. Okay, and rest of the memory is for the user, you can consider like that. So that's why the frame numbers 0, 1, 2 up to 10, these frame numbers are for the user, you can consider from the main memory. And I could see some different color pages here, right? So it belongs to processes, 4 processes. Process 1, the color is purple, you can see. Process 1 can be divided to pages like P0, P1 up to P5. So 5 pages are there. Then there is this brown color process P2, right? Orange or brown, you can say. And this particular process is divided into again 4 pages. The page size should be same. Okay, then another process 3 is there in the hard disk and assigned by the color red. One more process P4, okay, which is identified by the color green. So there are 4 number of processes in the hard disk, and my RAM is having only few pages from those processes. For example, orange, you can see page number 1 and 2. So from the process P2, okay, which is having actually 4 pages, P0, P1, P2, P3, but only P1 and P2, only this P1 and P2 are there in the RAM. Okay, rest of the RAM is occupied by other processes. Similarly, from the red color P3 process, P4 page is there and P5 page is there. Okay, so why it is like that? Because maybe these particular pages are already requested by the CPU to execute that process. Okay, and because it happens in a concurrent manner, some portion of the process P1 P2 is done, then some portion of the process P1 is done, some portion of the process P3 is done, some other portions of the process P4 is done. That's why it is like that. Now so the same thing here, page size will be equal to the frame size. Note that only some required pages are only fetched to the main memory. Pages may not stored in a contiguous manner, because this is a paging technique that we are following. So paging is a non-contiguous technique. So that's why the pages which belongs to the same process are occupying the memory in the main memory in a non-contiguous manner. Okay. Then you see here what happens. The CPU is currently executing process P2. Okay, we'll have a look in process P2 in the hard disk. It has P0, P1, P2, P3, 4 pages, right? So as if I see in the main memory, P1 is already loaded to the main memory, and then P2 page is already loaded to the main memory from the process 2. Okay, that's why in my page table also you see the 0 1 2 3 0 1 2 3, these are what, these are nothing but the page numbers, correct? These page numbers from the process P2. That's why the page table of P2 is having only 4 slots, because it is having 4 slots of pages only. If it would have belonged to process P1, my page table would have been a different one. Okay, so that page table would have 5 number of pages. Okay, 5 number of entries in the page table, whereas because it belongs to P2, it is having 4 number of entries. So as I told before, each and every process will have its own page table, correct? Now because page 1, okay, is there in the frame number 0 of the main memory, so this page 1 is there, is mapped to which frame number? Frame number 0 of the main memory. Similarly, page 2 is mapped to frame number 3. Sorry, here a simple mistake is there. So no mistake is there. Page number 2, this is page number 2, these are the page number, right? This page number 2 is there, is mapped to frame number 3 in the main memory, because it is there in frame number 3. And you see very carefully the valid invalid bit, because page number 1 and 2 are loaded into frame number 0 and 3, the valid invalid bit is 1 here, whereas the other two pages are still not loaded into main memory. That's why the valid invalid bit is 0 here. Okay, so that is the importance of the valid invalid bit. It will indicate, if it is 1, it will indicate that particular page is already loaded into the main memory. Okay, this is required for program execution, for the ease of program execution. Whenever the CPU will require some page, maybe that particular page is required in multiple numbers, right? So it will first check the valid invalid. If it is a valid invalid bit, it will first check. If it is 1, then CPU will understand that the page is already loaded. If it is 0, then page fault will occur and CPU will demand for that particular page. Okay, so let's assume process P2 is getting executed, yes, and pages P1 P2 are already present in the main memory. Observe page table, page 0 and page 3 of process P2 are not present in RAM, so their valid invalid bit is also 0. Then what will happen? Now because P2 is still executing, CPU will now suppose request the page number 3 of process 2. So page number 3 is this one of process 2. Okay, uh, and now what it will do, CPU will check entry in page table of process 2, whether page number 3, yeah, this is the page number 3, whether this entry is there, whether it is it will check the valid invalid bit. Okay, it's 0, that means it's not loaded yet. Okay, so what will happen, then the CPU will generate a trap signal. What is a trap signal? It is generated when a program requires system service. So when the CPU will generate the trap signal, it requires the service from the system that I need this particular page, okay, to be loaded from the secondary memory to the main memory. Okay, so what will happen? Swap in will happen. Okay, and to do that particular loading, okay, that is some work which is of in urgency in nature. Okay, that's why I need some more like some more power, okay, to execute that. that user process will change the mode to kernel mode. Okay, so that P2 process P2, which is a user process, okay, generally it will be in the user mode, but since CPU is requesting something which belongs to that process P2, okay, it will then change the mode to kernel mode, because in kernel mode there are more authority from the operating system, there are more support from the operating system. When that swap in will happen, okay, no other interrupt, low level interrupt can disturb this particular swap in. So in kernel mode, OS brings page 3 of the process 2 into the RAM, okay, and suppose it will bring that page 3 into which frame number, frame number 9. So immediately I will write frame number 9 in my frame number page table. Also I will change the valid invalid bit to 1, okay, and CPU's requirement is done. So now the process will change its mode back to user mode, okay, and now then CPU will now access this page 3 by referring page table entry. So CPU will see that this page number 3 is there in the main memory frame number 9, then it will go to the main memory frame number 9 and it will see whatever lines of code is written, okay, to execute that. So this is all about the scenario where what happens, where first thing happens is that page fault. CPU is trying to access a page, but the page is not available in the main memory. So then we say that page fault has happened, and when this page fault has occurs, process switches from user mode to kernel mode, and in the kernel mode the operating system fetches the required page from secondary memory to the main memory, okay. If there is free frame in the memory, then the required page will be placed in that frame. Yes, in the previous scenario I can see that my this 9 number frame, it was vacant, so that's why I have loaded it to my vacant space, okay. But we are not lucky always, okay. My RAM is not always free like this, because as I told, all the time some thousands of process in the background also is happening. So if there is no free space or frame, then existing page gets replaced with new page using the page replacement policy. So suppose all this one is also already occupied, this frame number 9, frame number 10 is also already occupied, and whenever I am bringing this page number 3, where I will put it then, or everything is occupied, what I will do, I will follow some page replacement policies. So for that also we have written, people have written lots of algorithm that which particular slot I should give. So using this page replacement policies will tell that you see this P0 process, page number P0 or page number P2 or page number P1, suppose these all pages belongs to process 4, right, and all are there in the main memory, and it's possible that this particular green color process has already executed, okay. This P1 green, P2 green and P0 green are no longer required maybe, okay. So you may replace these slots, okay. So the algorithm written in this page replacement policies will tell me that, okay. So existing pages will be replaced, and then those existing pages will be then placed back to the secondary storage, okay. The time required to service a page fault is called page fault service time. Again, these terminologies are very important, you have to remember it correctly. Now there are a lot of page replacement policies are there. Very basics are first in first out, then optimal page replacement, then least recently used page replacement policy, and most recently used page replacement policies, okay. So in your syllabus you have FIFO, then optimal, and then LRU. MRU is not there, okay. So but both LRU and MRU are of opposite nature, so you can still study it. So you see here, if there is a free frame and page fault occurs, then store new page with no replacement. Okay, obviously if I am having some free slots here, I will page fault will occur definitely. P3 is not there in the memory, so I need to bring it, but I will occupy the vacant slots. But if the all the slots are occupied, I will replace any of the pages. Okay, so what happens in FIFO, first in first out page replacement? If no free frame is available and page fault has occurred, then I will replace new page with the page arrived first. Okay, that means in this particular main memory, out of all the pages, which particular page has arrived at first, okay, in the very first time, that particular page I will replace. Okay, that is about the FIFO policy. Optimal page replacement is what? I will replace that page which is not used, which will be not used in longest duration of time in future. Okay, so in future, for the longest duration of time, whatever page will not be used, that I will replace in case of optimal replacement. So in this optimal replacement, the requirement is that I have to know beforehand what will come in future. Okay, which is actually not feasible. Okay, this optimal page replacement is practically not feasible to implement, because then I have to know all the future pages or processes that will come. Okay, so this is not always feasible. If I'm having limited number of processes and I know that all the processes, suppose there are only 5 processes to execute, okay, then I can go for optimal. I can see that out of those 5 process, which process space is will be used in the longest duration of time in future. Okay, but otherwise if it is not certain or not definite that only 5 process will be there, there may be more process in the future, which currently at this stage I am unable to tell, then I will not go for optimal page replacement. Then there is this least recently used strategy. What happens here? I will replace the least recently used page in the past. So in past, few pages are used and one new page is coming up. Now if I have to replace any of these pages, I will replace the one which is least recently used in the past. And MRU, most recently used strategy, it is simply opposite of LRU. I'll replace the most recently used page in the past. Okay, we'll see some example and then it will be more clear. So here there is this reference string is there. So what is this reference string? The CPU is suppose requesting the pages 0, then pages 1, 0, okay, 7, then 0, then 1, then 2, in this sequence. Okay, these are the pages you can consider, or the frames you can consider. Okay, the CPU is executing some particular process, or maybe CPU is executing processes, different processes, but it has marked these pages. Okay, these are the pages that the CPU is going to request. Okay, but in my main memory I am having only 4 frames. Okay, so I have to accommodate all these requests of the pages by the CPU with only 4 number of frames. Then how many page fault will occur? Okay, we need to calculate that as well. And if the number of frame is 3, if the memory RAM size is 3 only, okay, only 3 frames can be accommodated at a time, what will be the page fault? Okay, so let me explain this particular numerical. To solve this problem, for my ease of execution of this, I will try to have something like this. Okay, I'll try to have a diagram something like this, where you see here how many frames I need? I need 4 frames. So suppose this is my sorry this is my frame number 1. Okay, then my frame number 2, frame number 3, and one more frame is there, frame number 4, right? So these are my 4 frames in the main memory. Okay, now here let me just